So, all right, so these are the slides for chapter 2, where we're focusing on the hardware or control loop hardware. And so for this discussion today, we're going to primarily focus on the looking at control valve sizing and looking at aspects of the sensor system. So we're going to focus on the actuator component and really just selection of control valves. And then we're going to look at various aspects of sensors. And so again, the main things that you'll need to be able to do are size of flow valve or size a control valve for a specific process, and also size a sensor, typically for a flow process. Okay, so I'm going to skip through the history of the control systems. We discussed this briefly last time, but I have there's another video already online for this. And so we're gonna kind of move forward to control valves. Okay, so control valves are going to be part of the actuator system. So the actuator system consists of a variety of components. And typically in a chemical process, an actuator system is going to be a flow valve, or it's going to be a valve of some sort that controls a flow rate. You can have feedback control processes that use some other type of actuator component, such as maybe like an electronic heater. So there can be electronic components to systems that are used to change the manipulated variable instead of a flow valve. For biological processes, oftentimes there's these variable speed pumps where you can just change the flow rate by changing a setting on the pump, and all these are electronic types of control. Okay, for a typical flow valve, though, for a control valve actuator system, it consists of a variety of components. So one of the main component that we care about right here is the control valve is going to be what we talk about primarily. Also, what's going to be important is an IP converter. So an IP converter is something that converts an air pressure to a current, and then an instrument air system. So for a pneumatic valve, the pneumatic valve is going to open and close by a change in air pressure. So the system has to be connected to some sort of instrument air. There's an IP converter, and then there's a control valve. So it's important to know that, because sometimes you can have problems actually with the instrument air, right? And these are things that you can find out. And you can also have issues with IP converters. And typically, these are either going to work or fail. But here, we're going to look at the control valve. And so a control valve consists of a valve body, a plug and stem, and the actuator is what makes it move. And then the actuator, what makes it move, is going to be springs and air pressure. We don't necessarily mess with a lot of these things, and it's important for us to understand what size valve body we want, and also what's the shape of the plug and stem, because these are going to be what allow us to achieve a specific range of flow based on how a system is set up and working. So here's a schematic of a flow valve, or of a globe valve, and this is typically used as a control system. And so up at the top, there's an inlet for instrument air. And so you can see there's going to be a diaphragm. So the instrument air is going to come, and it's going to push against this diaphragm, and it's going to cause this spring to flex. So what you see is, as the instrument air increases the pressure, it's going to push the valve stem down. And as you decrease the pressure, the spring is going to push backwards and push the air up. So one thing that I want to note, especially for a valve system, is typically, because these operate based on, some of the driving force for this system is going to be the spring. So these control valves are typically going to be governed by what's called first order differential equation. So the rate of change in which the flow changes is going to be first order, because the response is typically governed by the performance of the spring. Okay, if we look down here at the bottom, you can see that we have the valve stem, or the plug in the stem, and then the valve body. So the size of the body is going to determine how much fluid can flow through the system as it relates to the change in pressure from one side to the other. And then also the shape of this, the shape of the valve of this plug is going to determine how the flow responds, or how the flow changes as this opens within the system. Okay, so also we can note that these valves can be air to open or air to close. And so we can come back and discuss that later. So you can tell if it's air to open or air to close by looking at the schematic and seeing, does an increase in air cause the valve stem to move up, or does it cause it to move down? And we'll talk about in a little bit how and why we might select different types. And these are things you probably already discussed, at least in the junior unit ops class. Okay, these are other examples of how some of these are schematics of the valve systems. And you can look at these on the slides or notes later. There's other types of valves in addition to globe valves, which are used for control systems. And an example is a butterfly valve. So a butterfly valve is it's what's called a quick opening valve. So what you can see here is for the butterfly valve, here's the cross section of the pipe. And the butterfly valve is like a flap that's inside here. So this is either going to be open or closed. So the benefit of these is that this valve right here, you can see is that as you turn this axis, the valve is going to quickly go from closed to open. And so it's going to be able to open and establish full flow in a matter of seconds. And these are important as they're used for safety bypass and other things where you might want a quick response of the flow to some condition. Another type of valve is like a pinch valve, and this can be used for slurry. So you can see here that, essentially by pushing down on this valve right here, well, this valve opens, it's going to allow this, viscous sludge or toothpaste or ketchup-like material to be able to move through the pipe. Again, we're not going to, for a butterfly valve, these are, typically fairly straightforward. It's either you need one or you don't, and the size of the valve is based on the size of the cross section of the pipe. Some valves might open or close a little bit faster. I don't see why that. I don't think that has a huge impact on the performance. Okay. Again, as we discussed some of these things, so the quick opening valve, these are used for safety bypass. Then these next two valves right here, equal percentage and linear valves, these will fall within the category of globe valves, the globe valves that we talked about. Okay, so the globe valves can be set up one of two ways. One is called equal percentage, and one is called linear. And we'll look at what this means. We'll look at some calculations used for each one of these. We haven't really given you any equations yet, so to describe what this means in detail, but what I'll tell you is that equal percentage valve, this is used for most processes because it gives the best characteristics for systems that have a varying delta P. So from your fluids class that pumps, for example, the pressure generated from the pump is going to vary depending on what the flow rate that's coming out of the pump. Right, so there's pump characteristics that's going to determine what the delta P is the pressure drop is a function of flow rate. In some cases, when pressure drop is not a function of flow rate, so for example, hydrostatic head, so if you have a gravity-driven system, the pressure generated is always going to be constant, and therefore we don't experience large changes in pressure drop. Okay, so what an equal percentage valve means is that the valve the valve opens an equal percentage based on what its current open position is. So if a valve is open small, as you open the valve, so if it's open a little bit and you change it, it only changes a little bit. If it's open a lot and you change it by the same amount, it opens by a lot. Okay, and we'll see how that works. A linear valve is a valve that just opens linearly as you open the valve. So the valve body and the response to the flow is linear. Okay, we'll see why this matters in a minute. Okay, so the main equation we need for size and control valves, or for looking at the performance of control valves, is the definition of CV. And this is something that you have seen before. So I'm going to write this, and I'm going to use these variables throughout the way. So the equation is the flow, FV. So this is going to be volumetric flow equals K, which is going to be a proportionality constant, times CV, valve coefficient, times the square root of delta P over rho. Okay, so this right here, this is all you need to know. And we're going to simplify this a little bit. So the volumetric flow rate. And again, the units on this are going to be, you can use whatever units you want on here, and that's going to determine what the value of this K is. For this class, again, now this is something that's really important. We're going to use FV in gallons per minute, and we're going to use delta P in PSI, and then we're going to use rho in specific gravity. So as long as you use these units, so as long as these units are used, the value of K is equal to 1. Okay, so and then we can calculate, again, we can calculate CV. So CV is a dimensionless number. And typically US vendors report the CV as a function of stem position. And again, this is valid for, again, as we said, K equals 1 if FV is in gallons per minute, PSI, and specific gravity. So in terms of unit conversions, if you're given other units, you can do the work to convert things to SI. My advice is just let's use everything in gallons per minute, PSI, and specific gravity. Now, you don't need to worry about PSIG or PSI because, again, this is delta P, difference in pressure. There's no, gauge doesn't matter. Okay. All right, so before we go too far, I'm going to discuss what this means for both linear and equal percentage valves. And I don't have a lot of room to write, so I'm going to try to do my best. So for a linear valve, CV is a function of X. So again, X right here, so CV is valve coefficient. X is going to be the valve position. So valve position can nominally go from 0% open to 100% open. So CV is a function of X equals CV max. And so what CV max is it's the maximum value of the valve coefficient when the valve is entirely open times X divided by 100. Okay, so if we think about what this means, for a linear valve, if the valve is, let's just say if it's 75% open, X is 75, therefore the value of CV would be 75% of the CV max, right? So CV is linear as a function of valve position. Okay, so that's what the linear valve means. So I'm going to erase this now. And we'll see what it means for equal percentage. So again, for equal percentage, CV is a function of X equals, well, we don't have a table, we don't have an equation for that. We are going to get this from a table. Okay, so I was kind of setting that up a little bit. So if we look at CV as a function of X for a equal percentage valve, when X is equal to 0, CV is 0. When X is equal to 100, my point went away. Okay, when X is equal to 100, CV equals CV max, right? So I know I have these 2 points on here, but an equal percentage valve is going to have a shape that looks like this. Okay, so, and again, this shape right here is going to depend on how the valve body is defined, and this shape is going to be defined based on the vendor. Okay, so we don't have a specific equation for this. We have to read this off a chart. Right, if we're going to do something for design, you can always take information that comes from the vendor, set it up to a plot, apply a curve to the plot, right? So that's something that we can do. And then we can use that equation for that specific valve to relate CV and X. But in general, equal percentage valves, these are designed for specific, or these are designed by the vendor, and we can plot it accordingly like this. Again, if we use this to size a valve, we have to just use the table to get the information. Okay, so looking at this slide right here shows CV as a function of valve opening for different sizes of particular valves. So the first thing that I want to say is that if you decide to use a linear valve, so if we use a linear valve, we can typically just go to these tables right here and take the value based on the size, the body size. So for example, if your process, you decided that you need a linear valve, and the linear valve, you need to accommodate a maximum flow based on the pressure drop that has a CV of, let's say 40, right? These would be too small. Maybe you would look at potentially this one right here, right? So for linear valves, we just use CV max based on 100% open for equal percentage valves. Because again, there's no reason for, for a vendor might tell you this is the maximum value for the linear valve, but you don't have to give this information in here because you just take the ratio. Okay. If you have but again, for this class, if you want to use a linear valve, just use this table and use CV max here to determine what that is. Okay, so now if we're using if we know we want to use an equal percentage valve, we would have to read it off this chart, for example. So let's just look, for example, if we think about a 2-inch body on an equal percentage valve, we can see the values here. So the maximum CV is 53. If it were a linear valve, the CV at 50% open would be about 27, 26.9. But we can see actually the CV is 11, right? So that means is that when the CV is changing at a much lower rate for small percent opens as it is for larger. And this is important because of how the flow characteristics and the pressure change with the system. Okay, so those are the two types of valves. So for control valves, we're going to use globe valves, and they're either going to be linear or they're going to be equal percentage. Now, the decision to pick between these two is going to be based on some criteria that we'll discuss in just a second. Okay, so this slide right here, there's a couple ways to plot characteristics. So one is called inherent valve characteristics. And what the inherent characteristics are is the performance if the pressure drop is constant, right? So again, we know the pressure drop won't be constant because as you increase the flow, right? So this axis right here shows the fraction of full flow. So at no flow relative to full flow, we know as you have flow through pipes and flows through systems, there is going to be a pressure drop. Okay, but this is a characteristic assuming that the pressure drop is constant, which you can achieve for certain systems. So the linear valve is going to look like this. Again, we have stem position on the bottom as a function of flow. So how does the flow change in response to stem position? If we have a linear valve, because again, CV, right, let me back up a second. Let's write our equation. FV equals CV times K delta P over rho. Let's make some simplifications here. So I'm going to say we're using GPM, FV is in GPM, and delta P is in PSI. Therefore, we know K is going to be 1. And let's think about this system as water, so rho equals 1. So to simplify our equation, right, let's just use FV equals CV times square root of delta P, right? So this would be for water using the correct units. Right, so if delta P is constant, if this term right here is constant, right, we know that these two terms should be linear for a linear valve, right? Because CV is linear with X. So if CV is linear with X, then also the flow should be linear with X. So that's what the linear looks like. Okay, the quick opening, we can think about this intuitively. So a quick opening valve, it essentially there's no real stem position. It's either open or not. So when the quick opening valve is closed, that means there's no flow. But then as soon as the quick opening valve starts to open, the flow is going to respond and give us nearly full flow. Okay, and again, this is just typically it's going to open quickly and the change in flow is going to be very fast. And so the shape of this is going to be depending upon, whether of the design of the quick opening valve. Okay, for the equal percentage valve, this line should actually go down to 0. Wait. Okay, I was a little too fast on the draw, so I'm going to have to pull this up again. All right. The quick opening, this line right here for the equal percentage should start at 0. And that wasn't a great drawing, but you can kind of get the point. It's going to start low, and then it's going to have this sort of an exponential shape. So what this means is that as we open, so if we're at small, so down here we're at small stem positions. As we open or close a valve at small stem positions, the flow doesn't respond that much. If we're up here at, again, high percent opens, as we open and close the valve, the flow does respond that much, right? So this would be the case, remember here, this is for if the pressure drop is constant, right? So this is just really to show how the flow responds, or how the stem changes in response, or how the stem allows liquid to flow through as you open and close the valve. Right, so this is one of them is linear, and one makes small changes at low flow rates and high changes at small percent opens, and one makes large changes at large percent opens. So that's what the equal percentage means. Okay, why this is important, and we're going to see this in a second. Equal percentage. I told you already. So far, it looks. You might be looking at this and saying, "Well, it looks like linear is going to be a better valve because." We just have a constant rate of change of the flow with response to stem position. But again, the problem is that most real chemical processes do not have constant pressure drop. And in fact, most real processes have a large pressure drop for their lowest flow rate relative. Well, let me back up. Most real processes have a large difference in pressure drops if you're at a low flow versus at high flow. So again, at low flow rates, the friction losses are going to be much less. And then the pressure generated by the pump are going to be much more. At high flow rates, the pressure generated by the pump is going to be much less, and the friction losses by the pipe and the fittings is going to be much more, right? Therefore, we expect a large change in delta P for low flow relative to high flow. So these types of equal percentage valves, these are used for 90% of chemical processes because of this factor. And the equal percentage valves were designed to give us a relatively constant change in flow with percent opening. And we'll see how that works coming up in the next few slides. Okay, so we'll start first. Let's look at an example where we have flow due to gravity. And what this means is that there's a constant hydrostatic head. If we have a tank right here that has a constant level in the system, and again, this height right here, the height of the fluid is driving the flow through this valve. So again, the pressure generated here is going to be constant. What we know though is that there's going to be, as the liquid flows through these pipes, there's going to be line losses, and the line losses will increase as you increase in flow. So we're not going to have a perfectly constant pressure drop at low and high flows, but the change should be small as long as this is a well-defined system. So we can generally get, for cases that's constant hydrostatic head, fairly constant or small differences in pressure drops between high and low flow. And we'll look at how this works. Okay, so if I lost you for a second, come back, and this is important because this is how I'm going to typically provide you with some data to use. I'm not going to ask you to calculate a lot of hydrostatic head or use pump curves to get the pressure generated. You'll have to do that for one of your assignments, but for a lot of the examples that we'll do, we'll have data that tells us what is the pressure as a function of flow rate. I'm not going to ask you to calculate a lot of the line losses, and these could be based on the friction factor, fittings, other things through the system, but you could be given some information about the system through plots as shown here. Okay, so this plot right here, what it shows on the y-axis is pressure change, or delta P. So this right here is delta P as a function of flow rate. Okay, so typically what we will have to know something. So we might know for our process, we want to operate between 100 and 500, right? If we know we want to operate between 100 and 500 gallons per minute, right, that'll tell us the range over which we want to operate, right? And so then we would want to calculate the delta P's for this process. So this line up here is what we call the pressure generated, or the positive pressures in the system. And the positive pressures in this system come from primarily the hydrostatic head. The next curve that we calculate based on knowledge of the process is the line losses. So this curve down here, this would be generally line losses. So at low flow, again, there's not a lot of friction. So this line loss can come from things like friction of the pipe, fittings like elbows, or other types of valves that are open in the system. And so these down here, these line losses, are essentially like the places where the pressure is dropped other than the control valve. So this is going to be all losses except for the control valve. So pressure generated, pressure loss. So what this doesn't show there is you can have other types of pressures in the system. So you could have a higher pressure at the source versus the sink, and you could either treat that as a positive pressure or a negative pressure, and possibly other things. Okay, so this is our positive pressure, this is our friction, this is our line losses other than the control valve. And then the last thing we do is we can calculate, right? So we can determine what is the valve delta P, what does the pressure drop have to be through the valve? And the pressure drop through the valve is just going to be the difference between the positive pressure generated, could be the pump or hydrostatic head, and the line losses from everything in the system other than the valve. So again, if we subtract these two, we end up getting this curve right here. Right, and so this curve right here, the valve delta P, and I know this is looking a little bit messy, but I'm just trying to highlight this curve a little bit. Okay, this is what we care about for selecting the control valve. Okay, so for the first thing, a general rule of thumb is that if we have a hydrostatic head, or if we have a constant pressure generated in the system, we'll benefit from using a linear valve. So linear valves are ideal if there's very small changes in delta P. So overall for this valve, you can see that delta P through the valve at low rates is about 13 for the system. Delta P through the valve at high flow rates is maybe 10, right? So about a 30% difference in delta P, which is not much at all. Okay, so my question for you now is that we now need to determine what size valve can give us this range of flow rates. Okay, so to determine what size valve we need to give in this flow rates is, again, we go back, FV equals K CV delta P over SG, or we should call this over rho, and rho is in SG. And again, we're going to say units using the right units, using water. We can get CV equals FV over delta P. Okay, there's a couple things I want to say about this. First, we need to get the maximum flow rate. So we know that we can get the maximum flow rate based on what is the delta P at the maximum flow rate required. But we can also we need to be able to calculate CV over the range of flow rates. Okay, so the way for going through and doing control valve sizing is we get our positive pressures, we get our negative pressures, and then we determine the delta P that has to be dropped through the valve. So sometimes there's a little confusion right here. It's like, well, how do you know all that pressure has to be dropped through the valve? And well, the answer to that question is, well, we know this is the positive pressure generated. At a certain flow rate, like 300 gallons per minute, right? We know all of the pressure that's going to be dropped through the line other than the control valve, which means that the rest of the pressure has to be dropped through the control valve. Because if it didn't, right, if the pressure that was generated wasn't equal to the pressure that was lost, we wouldn't be at steady state and the flow rate would change. So assuming we're at steady state at 300 gallons per minute, all of the pressure generated has to be dropped through the line and through the valve, so we know what it would be through the valve, right? And essentially you can open and close the valve to guarantee you get to that CV. Okay, so we get the delta P. Based on the delta P, then we can go ahead and at various increments, so at different flow rate values, we can calculate CV. So we can calculate CV for various flow rates, and then we can look at how that CV compares to other types of, to the charts that we might have available. So for this system, I already told you, we want to use a linear valve, and we want to achieve a flow range of 100 to 500 gallons per minute. what size valve do we need for the system? Okay, we can determine the size valve by just calculating CV at the maximum flow rate. Because if we can't achieve if the CV is not big enough at the maximum flow rate, the rest of it doesn't matter. Right, so at the maximum flow rate, FV is 500. The pressure drop up here is, what is it? About 10 at 500, maybe 11. Let's just say that it's 9. So I can take the square root of 9. So I have 500 divided by 3. And maybe let's just say instead the pressure is, well, 500. So what's 500 divided by 3? 166, I think. Anyone want to confirm?
Yep.
About that?
Yeah, that's right.
1 and 100 and 2/3. Okay, so now this is my max CV. This is CV max. Again, so now we can go back and we can look at our available sizes. So I said that we needed 166, and we come back and we look at this. These valves are all too small, so we would need a 4-inch valve to achieve that flow rate. Okay, if we said our maximum flow rate were 400, right, we could go ahead and do the same thing, and we would need, maybe we might need a smaller valve. Okay, so again, when we determine, the first thing that you need to be able to do, or the most important thing for determining for sizing a flow valve, is to first decide or determine what size valves will actually work. And that's going to rule off, a lot of the valves that are too small. Now, once you've ruled off the valves that are too small, you can, if you have multiple valves that could work, then we'll use some heuristics that we'll talk about later to decide which one is actually best. Okay, let's look at, so this case, so again, we calculated CV max. So I'll point out though that we also calculate CV max. We also can calculate CV for the different flow rates, right? So we have CV, we have delta P, and then we have FV, delta P, and we can calculate CV. So when we size a control valve, in this case, we might go for 100, 200, 300, 400, 500, right? We would read the delta P off the chart that we would get up here, and then this right here will calculate CV for the system. Right, so that's how we would do it. So we could calculate CV, and then we can generate the plot that's shown on the following figure. And again, we'll see why this is useful in a second. Okay, so now this right here, so tells us what's the installed flow rate as a function of stem position. Now I'm going to go back to this little table that I was saying. Once we calculate CV for each of the flow rates, and I should have made my table a little bit bigger, but I'm going to go ahead and write it on this side instead. So I know this might be a little confusing, but I think you can get the point. We can then calculate X. And then the calculation of X right here is going to be based on the known CV, right? So if it's a linear valve, and we know, so if it's a linear valve and the CV max is, we said 190, that was our max, or at 100% open. And we said we need a CV of 166 at 500 gallons per minute. So tell me, what percent open would this valve be at 500 gallons per minute?
166 divided by 190.
All right, so this would be 166 divided by 190. Whatever that value is would be the value of CV. So again, if we calculate, so any of these, so for all of these numbers, if we calculated a CV at 100 of 10, for example, or 20, it would just, the X percent open would be, 20 over 190, or whatever the value would be, right? So we can calculate the percent open as a function of flow rate, and that tells us what is the installed characteristics of that valve. Okay, and so this is going to be one of the things we work through on the homework. It's just kind of follow through this process, and you can set up these types of systems. So here we have installed flow rate. Now remember, the installed flow rate is essentially, maybe it's going to be given, right? And in other cases, I could give you a valve and I could say, tell me how this valve works over, whatever range of flow rates, and you just do a similar thing. Okay, so we have these flow rates, and then for this example right here, we calculated the stem position. Again, we first used FV, we used the flow rates, we read the delta P off the charts, we calculated the CV, and then we calculated the percent open. That's the process we went through. So now what we're going to do is for each of these flow rates, so for example at 100, we calculated the percent open. For 200, essentially for whatever these increments that we were given there that we used, we just calculated what the stem position was, right? And we plotted them on the line. And then once we calculate these, we can fit a line for them. Okay, so a linear valve is going to look like this. If we had instead used an equal percentage valve, the process is the same, except one small difference. Okay, when we calculate the CV here, right, we calculated the same CV was required. Up here it was 166. This was the required CV. Let's go back and look at, now we would have to use this chart right here to determine what the stem position is, right? We can't just take the linear ratio. We have to use the chart to take the stem position. So 166, if I look at this chart right here, and again, you can use this, you can do this linear, or you can do this any number of ways. 166 is pretty close to here. So this is probably going to be about, 88% open. If at some point on the system, like, 300, if we needed a much lower, if we needed a CV of, like 50, we again go down, read it off the chart, and then we would know that we would need to be about, 59% open. So for equal percentage valves, once we calculate CV, we use the chart to get the stem position. For equal percentage valves, we just use the ratio based on CV max. Okay. So we did that here also, right? So here's now we're looking at, going back here. So again, at 100, well, again, we would have to use different increments here. So again, if we used 100, we would have calculated this for equal percentage, same size body. 200, it would show up here, 300. And so maybe we might have to go down and do a calculation for 50 to get these points down here. So what you see for now, for an equal percentage, the shape of the curve, it's going to look like this. It's going to open a little bit at slow flows, and then it's going to open a lot at here. Now the problem with this is if we want to use when we use this valve in a control system, the controller is essentially going to output like a milliamp signal or an air pressure. So if you increase the air pressure a little bit, it's going to correlate to a change in stem position, right? So if the change in air pressure, if it's just, essentially it's going to be linear, because the control systems are going to be based on linear models. So a linear change in stem position is going to correlate to a linear change in flow only for a system that has a constant pressure drop. So this valve right here, essentially, if we change the air pressure, it's going to lead to about a consistent change in flow rate. So here we would expect, as we change air pressure, we get the right flow rate we want for the process. So that's what we want. We want a fairly linear, or as linear as possible, installed flow characteristic, or flow rate as a function of stem position. And what you can see is based on this example that I did, and I went through this in a little bit detail. What this example shows is that the performance of the valve depends strongly on what is the shape of this delta P through the control valve. If now instead, I'm going to figure out how to change the colors on the pen to make this more clear. I'm not exactly how to do that. Here's somewhere down here. We'll do that next time. But anyways, if the delta P through the valve instead looked like this, right? Now we're looking at really different, right? So down here, now we're looking at really different type of performance. The calculation would be different for all the points. And then these shapes, we'd see very different shapes here, right? So we can, if you want to do a rigorous analysis for linear versus equal percentage, you can just do this same thing for both systems and compare which one has a better performance and then select the one that has a better performance. If you're really doing this on a process and you're not sure, kind of on the borderline where, well, both of these valves would work, it might be useful to be able to go through this analysis, because the better performance you can get, the more efficient your control is going to be, the more money you're going to make with your process. Okay, so now we're going to go forward and look at pump-driven flow. So here's, again, this is going to be really the same example, so I'm not going to spend as much time. Here's an example of, again, we have delta P versus flow rate. And now what we have here is we have a pump-generated flow. So the pressure generated by the pump in this case is going to, again, start to decrease at higher flow rates. Again, line losses for this particular system, maybe there's more fittings and elbows, so we can see that the line losses are going to look like this. So what happens at the point right here? At the point where the line losses are equal to the pump generation, what happens here? What if we try to increase the flow rate? Okay, I saw a meme one time that said engineering classes were like Dora the Explorer. The professor asks a question, waits about 3 seconds, and then answers his own question. I'm going to try not to do that much. If you have any thoughts, maybe throw some ideas or maybe brainstorm. You don't have to answer, but maybe throw out an idea about what's going on, what's happening here. When we have the pressure generated equals the pressure lost, and we want to try to increase the flow rate. What's going on right here?
Would it make the flow like go in reverse?
Okay, so I'm glad you said that, because that's sort of like the intuitive thing that we start to think about. Like if there's more line losses, it would make it go backwards, right? So if here's the way I want to think about this question. Assume now we're operating in this system, right? We haven't considered the flow valve, so that means the flow valve is probably wide open because we're not considering the performance, okay? If we're operating at 22, if we're here, we're sitting here at 220 gallons per minute. So the flow is going forward at 220 gallons per minute going forward. We get to this point, right? If we try to go faster, we're not going to go from 220 pounds or 220 gallons per minute this way to all of a sudden turning around this way. Right? What's going to happen is we're just not going to get any higher flow rate. We've peaked out on the flow rate. So anything we try to do to get more, it's not going to be able to give us more. So we can't continue to go forward in this direction. If now we start to, if we're here now and we start to close the valve, what's going to happen? Like what happens when you close a valve, you know? The flow rate decreases, right?
Yeah.
Right, so we would just essentially, as we close the valve, we move backwards on this line losses, right? Because as we close the valve, we are increasing the delta P loss through the valve, which is going to have to bring us back. And then because we have gone to a slower flow rate, now the pump is giving us a higher pressure. Okay, so this point right here is essentially the maximum point that we can achieve based on the process as it is designed. Right, so if you try to go beyond this point, it's not like something magical happens. It's just that you can't get any more than that. Okay, so same thing we did last time. We have pump head, we calculated line losses, right? So we did that. Now we know that this right here is going to be the maximum. We can't, if your boss comes to you and now says, hey, I know you designed the system and you did it just like I wanted to, and you did it really well. We now need to do 250, so make it work. You're like, what? You're like, you can't. So what? I'll just throw this question out here. What would you do?
New pump.
Okay, new pump is an option. What are other options?
You could reduce your line losses.
Right, and so this question is a little bit ambiguous because you don't know what's the cause of the main line losses, right? So if the main line losses were because the pipe was too small, or was because you might have these unnecessary valves or orifice plates in the system, you might go back and sort of change some of those. But pumps are typically expensive. Repiping a whole plant could be expensive. So I mean, if it's a matter of doing those things, so again, you can consider what are these two things and what's the most economical way to do it. Okay, but we're not going to do that for now. So we have our pump head we get from our pump curves. We have our line losses. We calculated those both based on fluid mechanics. And now we can calculate, must be the delta P loss through the control valve. So the delta P loss through the control valve is going to look like this. So now if we want to go between, let's say 50 and 200, so 50 or 200 and 50, right? The delta P up here at 50 looks to be about 20. The delta P down here looks to be about 3. The difference now between the delta P is huge, right? So we can't consider this to be a constant pressure drop. So the general rule of thumb that the author says in the textbook is if the ratio is greater than, I think they say 4 or 5, use equal percentage. So 20 divided by 3 is like 6.7. That would mean we would use equal percentage. So, and again, I think really, if you actually do the rigorous analysis, the difference, they become about the same if your delta P difference is about 2 to 3. Equal percentage valve is going to work better in some cases. Linear valve will work better in others. A better, like an easier to use heuristic, and what you can use for this class is if you have pump driven flow, use equal percentage. If you have gravity driven flow based on hydrostatic head, use linear. Okay, so there's no reason to, you can calculate it and you can make a decision, but generally, if you have pump driven flow, you're going to have this type of behavior. If you have hydrostatic head, so you can use either one of those metrics to determine which one you use. Okay, so again, we would do the same thing that we did last time. We have FV, we have delta P, right? We can get this from the plot. We read this, we calculated valve based on taking the difference. After we get delta P, we calculate CV using the equation. Once we have CV, we get X, right? We can get X for linear and we can get X for the equal percentage, and I showed you how to do that, okay? Once we go through this example, like we just went through last time, is we can go ahead and plot flow rate. So again, remember this right here. Oops. These are given values. This right here, stem position, this is what we calculated. So we calculated this, and then we plot it. So for an equal percentage valve, if we go ahead and we plot these curves, what we're going to see is they're going to look something like this. For a linear valve, it's going to look like this. And the difference here is that we see is that a linear valve at low flow rates has a steep response, and at high flow rates, or stem positions, has a very flat response. So depending on where we are, the performance of the valve is going to change for a pump-driven flow type system. What you can see here is now this is not exactly perfect, but it's relatively linear over a large range of stem positions, okay? So pump-driven flow, equal percentage is going to give a more linear system. And again, you can do rigorous, if you're doing a real process, I might go through and do the rigorous analysis. For here, we can use that rule of thumb. A couple other things that are important. So other important heuristics is generally, we don't ever use a valve greater than 85% open. So the maximum stem position, okay, this is important. The maximum stem position that you are allowed to use for this class is 85% open. So this is the maximum allowable. Now, of course, if you're actually doing something, doing a process, and you kind of, open it a little bit more, what you see though is anyway, if you open a valve between like 85% and 100% open, the flow is not really going to change very much because the valve's pretty much already all the way open, right? And you've seen this before. You've opened valves and you've kind of established full flow. If you open the valve a little bit more, you don't notice any more change. That's because the flow characteristics aren't able to respond. Okay, the other rule is that, and again, the textbook says a couple different things, and I don't really care which one you pick on here. 10%, 15%. You cannot use a valve below 10% open. If you want to say 15%, the textbook says, I think 15%, you might say 10 to 15%. But in any case, you don't use a valve below these conditions. And the reason for that is if you design a valve to be open and closing in this range, what's going to happen is the valve is going to be slamming open. It's going to be opening and closing all the way. And it's going to wear the valve out. And again, that's not ideal. Okay, so this kind of shows, again, here's some of the heuristics. You can look at this slide. You know, again, characteristics are going to vary for linear and equal percentage valves depending on the flow characteristics and the pressure drop through the system as a function of flow. The textbook that we use says if the delta P at max flow over the delta P at min flow is greater than 5, use equal percentage. This number is probably closer to, I don't know, somewhere around 2 to 3, somewhere in that range. You can also look at another rule of thumb is if you look at the slope of the installed characteristic, the max slope over the min slope should be less than 4. I mean, it should actually be a little bit smaller than that. But again, you can't always achieve all of these characteristics for a given system. Okay, so here's what we mean, the slope of the installed characteristics. If we go back and look at this curve, we can take the slope at each point. So we can calculate the slope. Again, if we tabulated this data in Excel, you can take the slope just by taking the difference between 2 points. Okay, so if we look at this data right here and we take the slope of the installed characteristics as a function of stem position, remember the linear valve we saw was very steep at low stem positions or low flow and became very flat at high stem positions or high flow. And then we saw that the equal percentage valve, you know, kind of varied a little bit over this range between about, 10% and, 70 to 80%. And then once the valve gets all the way open, it doesn't change at all. Okay, so you can look at these two things. And so in this case right here, the ratio of the slope, at this condition, so 4 divided by 2, the ratio of the slope there is 2. Ratio of the slope here is 4. So this would tell us that our range of operation for this valve would be, about 10 to 75. For linear, we would run into that slope constraint somewhere around this range right here. So a linear valve is not going to work very well for the system. Okay, so again, some other information in terms of valve sizing. We sort of kind of said 15, you can say 10 to 15% open, 85% open, no more than 85% open at the maximum flow rate. Typically, when you're given a process, you're given a maximum flow, a minimum flow, and then a normal operation. At normal operation, the valve should be between 50 and 70% open. So again, you can use this criteria here is if you can select multiple valves that might work for a process, and one valve is 85% open at max flow, or let's say 80% open at max flow, and another valve is 50% open at max flow, you would select the valve that's 80% open at max flow. The reason for that is if a valve is only, let's say, half open at maximum flow, you're only using part of the valve to control the flow. If the valve is 80% open at max flow, you're using the whole range of the valve to control the flow, which is going to give you better resolution of control. Okay, so that's the criteria. If it's close, you can, you might pick and decide. But again, what you'll see is that, there's only going to be a couple options to decide. You want one that has to be, again, to find something that's 50% open or 15% open at small flow and 85% open. You might not, that'll probably be enough criteria to select the valve for you. Okay, so other criteria for a valve is going to be air to open or air to close. And so I'm going to ask you questions right here, and these are not hard questions. You should have seen this before, so maybe you can help me out so we can move forward quickly. Air to open or air to close kind of depends on what you want to happen when the air system fails, because air systems can fail. So if if a valve is operating air to open, as you increase the air, it increases the flow, right? So it will fail closed. Air to close would be a system that's open when it's closed, when there's no air pressure, and the air is used to close the valve and restrict the flow. So what's an example of a process that you would want to use an air to open valve or something that fails closed?
Some like dangerous chemicals, hydrocarbons.
Sure. If you have a valve that's controlling the flow of a toxic material into a process, you don't want that to be unrestricted into the process. I mean, in general, you might even just say that for a particular reactant going into a process. What's something else? I mean, there's something more. There's something really obvious that you don't want to fail. You want it to fail closed. You don't want it to be left open and uncontrolled.
Steam?
Steam, yeah. So if you're using steam to heat something, right, and you have a problem with your air pressure, and all of a sudden your valves die and your steam is going into your process, you're going to heat up your process to the maximum possible temperature that it can be, and that's not ideal. So like heating systems, because again, you want to leave systems at the lowest energy type state. So steam, air to close. Okay, so now that makes this next question easiest. What are systems that you want to fail open?
Cooling water?
Cooling water, right. So cooling water valve, you'd want to design it to be an air to close. And okay, now this, right, so these are, maybe hopefully a little bit obvious. Some things are less obvious. And it kind of it depends on, is something going into your system or is something coming out of your system, right? And then you can decide a little bit that way. The selection of air to open or air to close is going to be important because it's going to determine how we set up the controller, right? Controllers they output numbers. Like you can't tell it to switch between a positive and a negative number. So if an increase in the controller output causes a decrease in flow, that's very different performance than if an increase in air pressure causes an increase in flow, right? It just started pouring. So can you hear the rain in the background? You all hear me okay still?
No, we don't hear the rain.
Okay. Okay, some characteristics, and again, I want to maybe go through this a little bit quickly because I want to talk about sensors. Valve deadband, and again, we can look at some of these things. Deadband, it's like, here's the way I'll describe it. On a steering wheel, or at least on old cars, if you turn the steering wheel a little bit, your car might not respond a little bit, right? But you have to turn it a lot to get the wheels to turn. I know new cars don't work that way. Sometimes I give this example and people don't know what I'm talking about. But like if you look at like a riding lawnmower or something. So deadband is like how much you can increase your air pressure before the valve moves. Because if you just increase your air pressure a little bit, it's because of like, stiction and friction, the valve might not move a little bit. So you can kind of slowly increase the air pressure and eventually the valve's going to move. And so that amount that it has to change is called the deadband. In terms of process control, these are just things that we try to minimize. In order to minimize deadband, sometimes valves have what's called a valve positioner. We'll talk about these are important things to know whether or not your valve has these characteristics, because if your valve has these characteristics, it's going to affect the performance of the valve, which we'll use later when we talk about how we set our PID controller settings. So some of these things now is just more of being familiar with it. Okay, and I'm going to kind of go through these a little bit. When it comes to troubleshooting, it's useful to know the general performance. So a control valve typically has a deadband of 1 to 3 psi, time constant of 3 to 15. The control valve with a valve positioner is significantly improved. The deadband is typically on the order of 0.1 psi. So with a positioner, it's much faster and much less deadband without one. Again, you might say, well, why don't you just put a valve positioner on all valves? The answer is because it costs money. Okay, adjustable speed pumps are other ways to control the flow. I'm not going to spend time on this right now. You can review the slide. This is less important because it's pretty much, it's controlled in itself. Okay, so for sensor systems, I want to talk about some terminology first, and then we'll look at a flow sensor. Okay, so for this class, you should be familiar with sensors that are used to measure flow rates. So we'll have sensors for flow rates. That'll typically be an orifice plate. We'll have sensors for temperature, and you've seen some of these before, like thermocouples, thermistors, thermometers, pressure, level, and composition. So many of these you might have seen before already in unit ops with hardware exercises. Some important terminology, span. And some of these are a little bit obvious. Span is just kind of the range of the sensor. So if a sensor has a span of, well, let me say two things. So span is the range of the sensor, 0 is the minimum value, right? So if a sensor, maybe a thermometer, for example, has a minimum value of negative 20 degrees C, and if the range is 100 degrees C, right? Now we know about the performance of the sensor. So the sensor is going to go from negative 20 up to 80 degrees C. 80 degrees C will be the maximum. So the span will tell us, how much essentially the signal changes with degrees Celsius. Some of these, there's a homework problem where you look at, just applying this. So look over that, and then, these are maybe a little bit intuitive. Accuracy is a measure of how close the sensor is to the actual value. We typically assume our sensors are accurate, and if they're not accurate, they have to be calibrated. Repeatability is going to be something important. Later, we'll look at filtering. So repeatability is essentially how close the sensor gives us to the same measurement. So if we know that the system is at 50 degrees C and it doesn't change, the sensor is not going to say exactly 50 every time. It might say 50, it might say 50.1, it might say 49.7. So it's the repeatability is like the variation around the true measurement. Process measurements dynamics, so this is like the time constant, how fast it responds, and then calibration is modifying the sensor to make it accurately read the real value of the system. Okay, so for flow measurements, we use an orifice plate DP cell. That's the most common. There are other types of systems like magnetic flow meters, mass flow meters, Coriolis flow meters. I think our unit ops lab has Coriolis mass flow meters. For this class, we're going to focus on design of an orifice plate DP cell. But again, if you need to design a sensor, you essentially need to know what is the maximum minimum range of the measurements that you need to achieve. Find one that fits that criteria. And then essentially you want something that's as robust, so it's not going to wear, and as economic as possible. Okay, so let's look at the design of a orifice plate DP cell. And then I'll briefly go over how to design this, and then I might just leave the rest of the notes for you to review. So an orifice plate DP cell looks like this. So here we have our control valve. So this is where we're controlling the flow. For a flow controller, we'll have a set point. So maybe we want 5.0 gallons per minute. So if we want 5.0 gallons per minute, we have to be able to measure it. So we'll have a measurement system. So this right here, it's what's called an orifice plate DP cell. An orifice plate is essentially just a restriction to the flow. So you imagine you have a straight pipe that looks like this, and you put like a washer inside. So you have a straight pipe, and then you put a washer inside that has a smaller diameter. So the smaller diameter, so shown here, right? So here's the full pipe. Here's the orifice plate right here, right? So the orifice plate restricts the flow, and this restriction of the flow causes a change in pressure, causes a pressure drop right after the orifice plate. So we can measure the pressure before. So we can measure the pressure before the orifice plate and the pressure right after the orifice plate. And this difference, this delta P, is proportional to flow rate. And it's proportional to flow rate through an equation that I will show you in just a second. Okay, one of the things that's important to know about orifice plate DP cells design and such is that the more you restrict the flow, the higher the delta P you're going to measure, but also the more permanent pressure loss you're going to achieve. So typically, in terms of designing an orifice plate DP cell, you want the minimum pressure drop needed to accurately resolve the delta P, right? So we can't just restrict the flow a little bit, because you can't measure very, very small changes in delta P. We want to measure at least 0.5 psi, 0.1 psi. If you try to measure 0.00001 psi, you might not have a tool to be able to do that. Okay, so we accept the fact that by putting the orifice plate in here, we're actually doing something useful. We're measuring the flow, but we are also losing some pressure. So we're causing inefficiency in the system. The permanent pressure. So I'm going to give you an equation for this. So I'm going to give you an equation that relates delta P and flow to the system. In the spreadsheet that I give you, there will be a permanent pressure drop based on some of these conditions. So I'll give this to you. You can also Google permanent pressure drop based on orifice plate, and you can come up with correlations. There's correlations tables, all sorts of things that can approximate what this is. Okay, so what we want to do is we want to be able to determine two things. The two things that we want to determine is what is the size of this orifice? So how much constriction are we doing on the pipe? So what's the size of this, the inner diameter? And what is the differential pressure that we need to be able to measure for this process? So those are the two things that we need. And sometimes it can be a little bit of an iterative process to determine it. One thing I want to point out too is typically you would want your orifice plate DP cell to be, not right next to your control valve, because you want your flow to have enough time to respond. So typically this is a matter of, at least a few feet before the actual control valve. And also you don't want to put this flow meter close to an elbow or close to something else, because you want the flow going into the orifice plate to be fully developed. Okay, so this just shows examples like DP cells. So DP cells can be based on these little capsules where there's, based on pressure difference on each side, this diaphragm right here can flex one way or another based on pressure difference, and the flexion can be measured as an electronic signal. There's pneumatic force balancing. So based on a pressure difference down here at the bottom, if you're kind of following me, the pressure difference right here is going to cause this bar to move one direction or the other. And then there's an air supply that's added to one side that's going to compete and cause it to move back so that this stays straight up. And based on this air pressures, we can know what's the pressure difference between each side. So there's a variety of ways of measuring this delta P in the process. Orifice plates might look like this. So you have a fitting in your pipe, and again, it's just going to be like a little washer looking thing that we put into the pipe that restricts the flow. And these are very easily changed. So when it comes to reducing the delta P of line losses, maybe it might be as easy as just changing your orifice plate. Okay, so here's criteria, and then I'm going to quickly show you the process, and then we will wrap it up, okay? General criteria for designing. Okay, the general criteria for sizing the orifice plate with the differential flow indicator. We want our beta, so that we want the value we calculate for beta should be between 0.2 and 0.7. So this would be at max, and this would be at min flow. So the pressure drop at the minimum flow should be at least 0.5 psi. This could be, this can be relaxed a little bit if you have a good measurement of the pressure drop. The reason why we say this is because if this is too small, then it's just really hard to measure, and we don't have an accurate gauge on what it is. And then if practical, the pressure drop across the orifice should be less, so the overall pressure drop should be less than 5% of the line pressure. And this is general criteria to minimize the amount of energy loss associated with the system. Okay, so we want to try to achieve these. And so I have written a procedure for doing this. But also, so I don't think I have my, let me open up, let me get my book and let me just give you the equation for some useful equations that we need. And these are in textbook, and these are also in my notes that I have provided. So we have the ratio, the flow rate. So FV equals CD times A2 divided by, okay, I don't know if I'm going to be able to, okay, ignore that for a second. Let's go on to, I'm going to write it right here for you, and then I might erase it. So these are the important relationships that we need to know. So FV equals CD. So CD is the coefficient of discharge, and typically this is going to be 0.6. So you can always use 0.6 or 0.61 times A2 over divided by the square root of 1 minus parentheses A2 over A1 squared. Okay, so A2 is the cross-sectional area of the orifice plate. A1 is the cross-sectional area of the pipe. I don't actually remember what those are. I just know based on the formula, this right here has to be less than 1. And so this term right here, this is 1 minus. I wrote 1 plus. Okay, 1 minus. And now multiplied by square root of 2 G sub C delta P over rho. Okay, so again, we can see now here that the flow through an orifice plate is governed by this equation. So this is flow rate in gallons per minute, or flow rate, and this is delta P. What I will say is, you know, this can be a unit conversion nightmare. I don't know if you've experienced that before in the fluids class. One of the things that I would recommend doing is just writing out this equation with an example, with showing the necessary unit conversions, and that way it makes it a little bit easier to apply. And there's examples in the textbook, and I think there's an example in the notes that I have. If not, I will definitely make one of those available. Okay, so also what we know is beta equals the diameter 2 over diameter 1. So this is the diameter of the plate over the diameter of the cell. And if we rearrange this equation, and this is the only time I'm going to do it, but I'm just going to do it now. So you have it. So beta equals the 4th root of FV squared over FV squared plus 2 times CD squared times A1 squared times GC delta P over rho. Okay, so beta equals FV. So, okay, what we can see here now is that depending on this right here, so this is our flow rate, we know that the flow rate's going to vary and delta P is going to vary. So these two things are going to change. So we can calculate, essentially our process is we're going to calculate beta at the maximum flow and then look to see if it applies and works well at the minimum flow. Okay, so that's going to be our general process. What we can see here though is that if we calculate, the important thing is now that we have this equation right here, we can see if we calculate something that's too big or too small, we can see how to change it. For example, if we're given a orifice plate and we see that the beta is too big at the maximum flow rate, we can see how to change. We might change delta P. So if we can make delta P smaller, making delta P smaller is going to make beta bigger, or making delta P bigger is going to make beta smaller. Right? So we can inspect the equation and see how to make some changes. This might make sense in just a minute. Okay, so here's our process for sizing an orifice plate diameter or an orifice plate DP cell. I'm going to start by erasing this to give me some space, and I'll put a little bit of I'll put an example on here too, just to show. Okay, at least work the homework problem that works through this, and that'll give you a little bit of an idea how to do it. So how to size, and this is my process, and it's kind of fail-safe. It mostly works. The first step is calculate the Reynolds number, and this has to be turbulent flow. So I think the book says maybe 10 to the 4 to 10 to the 7. And again, if you don't have the right flow, then that means is you can't use the orifice plate DP cell as an accurate flow measurement. So you'd have to pick something else. And so really your sizing would be done there anyway. Okay, so now in terms of sizing, we're gonna say I want my delta P max. So I'm just gonna start here. We can start here and we can change things using judgment later. I'm gonna make my delta P max equal 0.5, so 5% of the line pressure. So whatever the line pressure is. And so as an example, I'm gonna use a line pressure of approximately 50 PSI or PSIG. Okay, so what this means is that, okay, we know, or we're told that we want the pressure drop through the orifice plate to be no more than, so it must be less than 5% of the line pressure. And so 5% of 50 is, what would that be? 2.5. So this would be 2.5 psi. Okay, so now the third step is we select the delta P of the DP cell. So again, the DP cell is going to be an instrument, it's a sensor, and instruments have ranges that they can operate. They have a maximum and a minimum. The minimum of all DP cells is going to be 0. Okay, so we need to pick a DP cell. So if the maximum DP that we want to measure is 2.5, the DP cell needs to have a maximum of greater than 2.5. If the maximum of the DP cell were 2.5 and we got to 2.5, we don't know if we would be greater than that or not. So the general heuristic that, at least as they mentioned in the textbook, and again, this is something that you can relax a little bit if you need, but just justify it. So the general heuristic is that the delta P of your DP cell should be, or the maximum that you measure your flow should be 2/3 of the DP cell. Okay, so in other words, so this right here, our maximum, this right here, DP max, this right here is maximum DP of orifice plate at, or maximum DP through orifice plate at max flow. Okay, DP of the DP cell is the nominal measurement of the DP cell. So the heuristic is that this value right here should be 2/3 of the DP cell. And what that does is it makes sure that as you get close to it, if you get over the maximum pressure drop, you can still measure that with certainty. And I might say, I think 0.7, 0.8 might be okay also, but again, for this class, I just try to stick to the heuristics that they talk about. So my nominal value of the DP cell right here would be 2.5 divided by 2/3, and this is going to be something like 3.73. Okay, this should be 2/3. So your maximum, this should be 2/3 of the nominal value of the DP cell, because again, DP cell, this is going to be instrumentation that we're selecting. We probably can't buy this. No, they're not going to sell something that has such a weird DP maximum. So therefore, we're going to have to pick something. So maybe let's say our options are 3 or 5. Okay, if we picked one that's DP max of 3, so again, at this point, we have to make a selection, and this is going to be based on information available. I would tell you, like if this were a test or something, I will tell you these are your available DP cells that you can select, and then you select one and justify why. The justification for why would be this exact process we just showed. Okay, so if we selected a 3, now our DP max, our delta P max would be 2.1. If we selected here, our delta P max would be approximately 3.5. Right, but this is, so the thing here is, this is okay. Our maximum, just because this is the maximum that we should be measuring on here, doesn't mean we can't use it. So we could use either one of these. So here's the trade-off. Okay, if we select this one, right, the maximum, the range, the resolution of our sensor is going to be less because it has a larger range, and we don't need to use that whole range. If we select the smaller one, we're going to be able to use the whole range, right? But then we're going to have to make an adjustment here. So for this example, let's select this one right here, right? And so if I select this DP cell, now my DP max at my maximum flow rate that I'm going to use is going to be this. So this right here is what I'm going to use for delta P max. All right, so this is what I found, what I calculated here was this, remember what I said is this is the maximum pressure drop that we should allow through the DP cell. Just because it's the maximum doesn't mean we should have to use it. It means we can't use something larger than that. Okay? This right here is the maximum pressure drop that we should allow through our DP cell. Just because it's the maximum that we allowed to the DP cell doesn't mean we have to use it. So the point is we could use either one of these for the design of the system. The trade-off is the larger one's going to have less resolution. Okay, the problem now with me guessing to use a smaller DP cell is that if my delta P, maximum delta P at max flow is 2.1, this is going to make the DP, the pressure drop at lower flows is going to be smaller, and it might be too small that we could measure. So that would be something that we'd have to check. Okay, now that we've done this, step 4, now we're pretty much done. We calculate beta. So again, beta equals, now so calculate beta at max flow. Okay, so what that means is that maximum flow, I didn't necessarily say what maximum flow was for this case right here. Maybe we'll say 100 gallons per minute. So this is FV max, and then we would use delta P max. Remember, delta P max is going to be this 2.1. It's not going to be the nominal value of the DP cell. Right, so these things right here, we put in the equation that I erased, and we go ahead and get beta. Okay, so now the thing is if we calculate beta, and if we calculate beta that's greater than 0.7, that means we'd have to use a DP cell that has a larger range so that we can bring that beta down. So we'd need a larger pressure drop in the beta term to have a smaller beta, or to have smaller beta. If beta is less than 0.7 at the maximum flow, that's fine. Then we would go down and calculate beta at the minimum flow. And so if we want to put the last step, check beta, oops. So here, check beta at min flow. And again, make sure it's greater than, so beta greater than 0.2. All right, so that's the general process for sizing the orifice plate. If you can get it to work at the max flow and you find something that's typically close to what that is, again, you might have to make trade-offs here. Okay, so that you can make decisions. It's not, the problem or the difficulty sometimes with sizing control valves, sizing orifice plates, is there's multiple correct answers. So it's important to justify what you're doing, why you're selecting a condition for a given process. And again, if you just go through the process that we outlined for the control valve and for this one here, you'll be pretty good. Okay, I think I kept you a little bit long just to kind of quickly look over some of the rest of these slides. Just give you information about the rest of the different types of sensors. There's some important information in the textbook. So one of the things is maybe you can visit table 2.3. I will put this up on Canvas at least so that you have this information. Table 3 just tells us the performance of different types of systems. So I'm going to stop sharing now and come back here. I kind of skipped through some of that last stuff. I really wanted to focus on the two design things for this chapter and not spend a ton more time on there. So hopefully find that useful. Look at the homework problems there. The worst thing about all of this stuff, like the worst thing about the orifice plate, is the unit conversions. And so you don't have to reinvent the unit conversions every time. Just do it one time, and then you'll know the things that are in there. And that's all. I have some notes, and if the notes that I have aren't on Canvas, I'll put them on there because they're kind of useful notes for just doing at least the orifice plate calculation. Do y'all have any questions or anything?